go 0.5 minus 6.4. Or if they do that, if they do 0.5 minus 6.4, then at the top, it has to be 525 minus 2000. Okay, they need to be consistent throughout. Like if they're starting with 2000, then this 2000, whoopsies, went ahead instead of behind. This 2000 goes with 6.4. Okay, so basically they have to be consistent in the direction they go. And so, yes, they put in the values, they do the calculations, and you see they get 250 meters per second as the average velocity. So in 1 second, it goes 250 meters, which is about, well, not about, it's 25% of a kilometer, which is really fast in just 1 second. As it says here, this is an impressively high land speed. So this is 900 kilometers per hour or 560 miles per hour. So they're doing a conversion. They're going from kilometers to miles. To do that, if you divide 900 divided by 1.6, you should get 560. So yes, much greater than the typical highway speed limit of 27 meters per second or 96 kilometers per hour. But yes, considerably shy of the record of 343 meters per second or 1,234 kilometers per hour, which was in 1997. So yeah, this is a jet car. So, it's a jet powered car. So it has a lot of power. So it makes sense. So yeah, this is one of the reasons why, okay, we make graphs like this. Like with this graph, position over time, we can calculate the average velocity. Gives us useful information. Okay, and so yeah, here they're showing that jet car displacement. Okay, where over time it goes really quick. And well, we'll see, okay, that there are ways. So this graph is not linear. Okay, and so this is the point uh, of how you can calculate instantaneous velocity. Okay, because again, here with this straight line, the velocity is constant. Okay, it's just traveling, sort of like at cruise control. Like it's always traveling at this velocity no matter what. Of like beginning to end, it's going at uh, uh, 250 meters per second. So all along this line here, it's always traveling 250 meters per second. Okay. But for this one, okay, how do you calculate the instantaneous velocity? Okay, whereas it says here, the diagram shows a graph of the position of a jet power car during the time span when it is speeding up, when it's accelerating. Okay, so the velocity is not constant. Okay, so the slope of a distance versus time graph is velocity. This is shown at 2 points. Instantaneous velocity at any point is the slope of the tangent at that point. Okay, so what they're doing when they say tangent is they draw a line. They draw a line that just goes right through one of the points on the graph. Okay, and then that tangent line we can calculate the slope of that tangent line that's just touching the graph, and that will give us the instantaneous velocity. The velocity that the jet-powered car is traveling at that point in time, which in this case, it looks like that's at around 25 seconds. Okay. So again, another reason why we use graphs like this. Okay. And then, yes, you can see that this is pretty much similar to what we've shown previously. So it's similar to this graph, at least part of this graph, where traveling to school, but now it's traveling back, where graph position versus time for the drive to and from school. Okay, where yeah, over time, but then your position. So here, this is a good example of like distance versus displacement. Okay, where you're going to school, and then you're driving to school, and then you're driving back. Okay, so your position, you travel 5 kilometers to school, but then you drive back home, so it's another 5 kilometers, but you ended up back at where you started. Okay, so you ended up back at zero. Obviously, on the x-axis, time is always moving forward, and so it's just the time really changed. You went 20 minutes, but you ended up back at the same place, so your displacement is zero. Okay, so we've talked about speed, we've talked about velocity, we've talked about distance, we've talked about displacement, and now what about acceleration? We're going to get into a little bit about acceleration now, but then in the next chapter, chapter 3, which we might be able to start today, we're going to do the whole chapter pretty much on acceleration. Okay, where acceleration, it might seem like a simple thing, but it's actually, a little bit complicated, not too complicated. You know, ultimately, as it says here, acceleration is the rate of change of velocity. So when your velocity is changing, you're accelerating in some fashion. So yes, we examine graphs of position versus time. Now we're going to build on that information as we look at graphs of velocity versus time. Velocity is the rate of change of displacement. Acceleration is the rate of change of velocity. We will discuss acceleration more in depth in another chapter, which is the next chapter. So here, we're graphing velocity, okay, versus time. So it's no longer position. It really, but time is still on the x-axis, but velocity is on the y-axis, the horizontal axis. Okay, so what they're showing here is basically it's again that drive to and from school. Okay, so as it shows here, 20 minutes in total. Same thing for this one, 20 minutes in total. But now, okay, what they're showing is the velocity on the y-axis, as in to go to school, you just started your drive and you drove half a kilometer, yeah, kilometer per minute. So that's the unit that they're using. And so you had a constant velocity there going to school. Okay, but now something maybe interesting happens that maybe we haven't seen before. Of here, uh, it's negative 0.5 kilometers per minute. And so this is the drive back home. We call it negative velocity because you're going in the opposite direction. Okay, so the sign changes of like to school plus, and then from school to back home minus. But you can see that the overall magnitude, it's 0.5. All it is a change in direction. Pretty much like, well, I drove 0.5 kilometers per minute to the left, and then now I'm driving 0.5 kilometers to the right, or in the negative direction. And it's pretty much represented sort of here. You can think of it of like positive to school, and then negative. Okay, it's decreasing back home from school to home. So that just we're going to see that there are reasons why we graph velocity on the y-axis. Okay, so as they say here, we can see that the average velocity for the drive back is minus 0.5 kilometers per minute. So but what if the velocity is not constant? Okay, because pretty much in the real world, velocity is almost never constant. Uh, even if you yourself have ever been driven to school, okay, you didn't just start the car and then you immediately start off at 0.5 kilometers per minute. It's like, no, you had to accelerate to get there. Okay. And so going back to our example of the jet car, okay, this is what acceleration looks like of now. Uh, Now the velocity is changing. Okay, where you can see we know the velocity is changing because the slope is changing. Okay, where here go back to this one. It's a straight line. Okay, and so if it's a straight line where you have position uh, on your y-axis and time on your x-axis, that means that no matter where you are on that line, okay, your velocity is the same. It was calculated at 250 meters per second. But now, going back to this one, since it's not a straight line, okay, we are graphing displacement on the y-axis and time on the x-axis, but now it's no longer a straight line. So what's happening? What's happening is the velocity is changing. Of the slope here, okay, the slope here is different than the slope here, okay, and therefore the velocities are different if I calculate it. Where, as it says, a graph is shown of the position of a jet-powered car during the time span when it is speeding up. The slope of a displacement versus time graph is velocity. This is shown at 2 points. Instantaneous velocity at any point is the slope of the tangent at that point, which, as explained earlier, if you want the slope at that specific point, you just draw a tangent that just barely touches the point that you're interested in, and then you can calculate the slope from that. Okay, so now here, okay, here is where you can graph. We're going back to graphing velocity on the y-axis, the vertical axis. Time is still on the x-axis. And so shown here, okay, just as when we, for this one, if we have displacement on the y-axis and time on the x-axis, if we calculate the slope, we get velocity. So we get information by calculating the slope when we graph things. And then similarly here, okay, but now we have a velocity on the y-axis and time on the x-axis. Okay, if we calculate the slope, okay, this says a here, we get the acceleration. Okay, as in we now get information from the slope. If we calculate the slope, we get acceleration information. Okay, so to like summarize, if we graph displacement versus time, get the slope, we get velocity. If we graph velocity versus time, okay, we get the slope, we get acceleration, the change in velocity over time. As in, so from here to here, it's a change of about 20 meters per second, or we're accelerating at 20 meters per second squared. As it says here, if we take the slope of the velocity versus time graph, we get the acceleration, the rate of change of the velocity. And if we take the area under the slope, we get back to the displacement. Okay. So again, some of the reasons why we make graphs like these. And we're going to be seeing a lot of graphs. Well, not quite a few graphs, not a lot, but we'll be seeing graphs pretty regularly as we go throughout the course. So want to get used to seeing them. So as it says here, most of the velocity versus time graphs. So this is terminology. When they say velocity versus time, uh, it goes y-axis versus x-axis when we talk about graphs, as in velocity versus time. This is velocity y-axis, time on the x-axis. We will look at they'll be simple to interpret. occasionally we will look at curved graphs of velocity versus time. More often, these curved graphs occur when something is speeding up, often from rest. Let's look back at a more realistic velocity versus time graph of the jet car's motion that takes this speeding up stage into account. Okay, where again, if you're a jet-powered car, okay, you're accelerating pretty quickly. And so what they're showing here, okay, is the acceleration, that change, that sharp change in velocity during the beginning, during the first, about 30 seconds. The velocity is pretty much changing throughout most of the time, except, okay, if you look at about 50 seconds, okay, you have this like flat line. That means that it's pretty much it reached its maximal velocity. Okay. And then it's just going to, it's going to stay there until it decelerates or slows down or stops. So what they're showing here is this rapid acceleration. Okay, you can see that, during the first 10 seconds, okay, if you look at the slope, how steep that line is, it's a pretty steep line. As opposed to here, okay, it's still pretty steep, but it's not as steep as, and if you look at the slope from 0 to 10 seconds, uh, it's uh, it's much sharper than the slope from 10 seconds to about 40 seconds. So what this is showing is like it accelerates really quickly during the first 10 seconds, or basically it changes its velocity during the first 10 seconds, and it changes its velocity really quickly during the first 10 seconds. And then after 10 seconds, it's still changing its velocity, it's still accelerating, but it's not accelerating as quickly as it was then in comparison to the first 10 seconds. Okay. And what they're doing here is, yes, they're drawing that if you want to get the instantaneous velocity at that particular point, it would pretty much be the point right here at about, 20, 25 seconds. Okay. You can draw that tangent and calculate that slope of that black line. Okay. But if you do the same thing, from like 0 to 10 seconds of, let's say I wanted the instantaneous velocity, or rather, yeah, the instantaneous velocity at 5 seconds. Well, if I draw that tangent to the line, it's going to be way more steep than the one at the 20, 25 seconds one, because again, the acceleration is much greater during the first 10 seconds than after that. And then, yeah, like I said, after about 50 seconds, it pretty much reached its maximal velocity. And then it's just going to stay there until it basically stops or slows down. So that's pretty much, velocity, speed, distance, displacement, and a little bit of acceleration. And then the graphs of how we represent those things. So that wraps up chapter 2. Okay, and now we're going to get into chapter 3, which we've already been talking about acceleration, which is just a change in velocity. But now we're going to do a deeper dive on acceleration, and how do we calculate acceleration, not just from a graph, but from a word problem. Like if they give us this problem, this word problem, what are the formulas? And we're going to see that there's multiple formulas for acceleration. So they're showing this plane here, okay, and what they're showing this plane landing, okay, and it might not seem, okay, it might not seem like the plane is accelerating, but as it says in the description, it is accelerating, but its acceleration is in the opposite direction of its velocity. Like it's traveling at a certain velocity this way, but it's accelerating in the opposite direction. It's a little hard to wrap your head around it, but you'll see it as we go. But yes, this is technically speaking a form of acceleration. So so pretty much, it's similar concepts to what we've seen so far, but now we're doing it in more detail. Okay, we're going to walk you through how to calculate acceleration from the examples. So, what does negative acceleration look like? So this is what they're talking about when we talk about negative acceleration. Of your acceleration can be moving in the same direction as the velocity, which is pretty much shown in figure A here, and acceleration, as we will see. Acceleration is also a vector quantity. Okay, it has magnitude and direction. Okay, and that's why it's represented by these arrows here. Okay, this yellow arrow for both of them for acceleration, it has a direction. Accelerating to the left here, or accelerating to the right, or accelerating to the left, or accelerating north, or accelerating south. Okay, because acceleration is a vector. So this figure shows a car with a positive acceleration and with positive acceleration in A and negative acceleration in B. And so obvious, or maybe it's not obvious, but hopefully you recognize that if the acceleration is in the same direction as the velocity, the car is speeding up. Okay, it's getting faster and faster, basically. But if the acceleration is in the opposite direction of the velocity, then as it shows here, the car is slowing down. Or another way to say that is the car is decelerating. Okay, and just as we can calculate an average velocity, which we have seen before, we can calculate an average acceleration. Okay, and that's what they're showing here in this formula, which is pretty similar or pretty close to what we've seen before when it comes to calculating velocity. When you want to calculate average velocity, it was delta d over delta t, but now for average acceleration, it is delta v over delta t. Okay, and yes, the SI units for velocity are meters per second. And as we'll see, and as they're saying here, the SI units, okay, the System International units for acceleration are meters per second square, which is pretty much saying that, every second, potentially our velocity is changing. And that's why it seems maybe a bit silly to think about it, but uh, it makes sense not only mathematically, but it makes sense conceptually. Because again, acceleration is a change in velocity. Okay, so you can be changing your velocity every second. Of second number 1, I'm going 10 meters per second. And then second number 2, I'm going 20 meters per second. So then my change in velocity, my acceleration, is 10 meters per second squared. Of in 1 second, I've increased my velocity. Or every second, I've increased my velocity. And that's why it's meters per second squared. Okay, so walking you through an example. Okay, this is where we'll finish off for today, where a subway train accelerates from rest to 30 kilometers per hour in 20 seconds. What is the average acceleration during that time interval? Okay, and so they walk you through the strategy of a simple sketch. Okay, so as they say, the subway train accelerates from rest. So it starts off with no velocity. Okay, you're starting off with pretty much staying still. And then, okay, the train speeds up to a maximal speed of 30 kilometers per hour. And then they're asking you, what's the acceleration? Okay, so they walk you through the steps to go through of convert to units of meters and seconds. Yes, this kilometers per hour is not appropriate. As mentioned, we always want to use SI units. So we want to convert units to what they should be. We want to determine the change in velocity, determine the change in time, and then use those values, basically plug them into this formula here. So basically we want to find our delta V, and we want to find our delta T. Okay, so they walk you through that. So identify the knowns. What information are they giving us in the problem? Okay, and as they say, be sure to read the problem for given information, which may not look like numbers. When the problem states that the train starts from rest, you can write down the initial velocity is 0 meters per second, right? So when they say from rest, that's why I mentioned the train is staying still. It has no velocity. So it starts off as 0 meters per second. Okay, so therefore, the V0 is equal to 0.